velocity. That requires us to do something else besides look at the shape of the track. So that's what we're going to solve now. Okay, so we got h, we got r, we got theta. We know that angle. Okay, so we're doing all those things. How do we do it? Well, we go ahead and put in the kinetic energy. What is it? Read my subscript. Final kinetic energy. So that's just 1/2 mv. Final, and I'll call it position b. So say position b squared. Okay, great. Now we're going to add the potential energy to the spring. There are no springs, so we're not going to bother with that. But there is some gravity. So now we have some choices to make because the absolute value, or I shouldn't say it that way, the actual value of the potential energy to gravity depends on our choice of where we want to call zero potential energy. I think in this problem, well, in a lot of problems it might be natural to just call the ground zero potential energy. I'm going to label on my diagram so I don't forget. So I'm going to say PE gravity equals 0 at this point. That's my choice. It's just like choosing my axes. You don't get to do that with springs. The zero potential energy for spring is at the equilibrium point. But for gravity, you have a choice. So let's take it down there. So in that case, what's the potential energy? What's the initial potential energy then of this guy? MGH. You bet. And it's positive, right? Remember that there's I'll go back to that minus sign thing from last lecture. But the higher you go, the higher your potential energy is. And remember, that means that if you start at the ground and you go up, gravity did negative work on you as you went up. And so some students are bothered by that. So, well, that doesn't make sense. If gravity's doing negative work, why does that result in positive potential energy? The way to think about it, I think, is that in order to fight against gravity, to lift yourself up, either you have to start off with a lot of kinetic energy and expend that kinetic energy to fake gravity, or somebody's got to push you. If I use my hand and fight against gravity, well, my pushing I'm doing some work. The work I do against gravity is positive. I'm doing positive work on the shock to lift it up. And that positive work gets stored somewhere. It gets stored in the form of gravitational potential energy. So that's the way to think about it. So that means that this high point up here is going to be a positive potential energy compared to the ground, because we just said to make that 0. So I get a positive mgh. All right? And there's no other terms here. And then right here, this is what I call final. I might include this just to remind me. The one common mistake, certainly the mistake I most often make when I do this stuff, is I put the initial values over here and the final values over here, and I get my minus sign wrong. Yeah. Absolutely. Yeah, the question is, will the potential energy be different at 2 points? Actually, they might be the same if I chose theta and r in a mischievous way, so it's exactly the same. But for randomly chosen r, theta, and h, they're going to be different. And we'll have to calculate. And it's going to show up not in this term, but in the next term, in this guy. And I'm going a glacial pace with this. You're thinking, well, you've been up by now. No, I just haven't gotten it yet. So it's going to show up right here. Right? So what is the kinetic energy? It's going to be 1/2 mvd squared. There's no spring, so I just put in the. So now it's going to be mg times some other h, right? Some h at point B. And because of the way the problem was specified, I got to calculate it. It didn't tell me what the height was. But don't be fooled by that. Just figure out what it is. Oh, yeah. Oh, did I put it? I told you I made this mistake. Awful. Ah. Yes. I'm sorry? So you're right. My mistake is more profound than this. So I'll go ahead and do this. So I think I was right with the world. But you might say, well, wait a minute. So what do my terms mean? I've been given the problem a variable that I called h with no subscript. I put it in the wrong spot right here, and then decided, okay, well, let's do this. Let's keep my head clear and just go ahead and use b's to indicate, like, let's say h sub b we have to calculate. H sub a is going to turn out just to be, that's going to turn out to be h. So in fact, I was just telling you the mistake I was trying to make, and I made the mistake unintentionally. But yeah, that's the mistake I habitually make with these things, and that's why I'm really explicit about these things. I check them at the end of my equation to make sure that the final situation is b. So yeah, thanks for keeping me honest. My b's go to the f, the a's go to I. This all equals what? Now it equals the work. So before we plug in specific values to these guys, then what's the work going to be for the roller coaster? So how many forces are acting on this ball, or whatever, the roller coaster cart as it travels down here? There's gravity. But what else is there? There could be friction, but let's say that there's no friction. Let's say that the problem tells you, assume force friction is 0. Okay, no friction. So what other force do we have? Normal force. In principle, then we could get a work, and that's an external force, right? My system consists of the ball, or if you like, the roller coaster carts. You know, like that's the system. So it is an external force, just like gravity is the normal forces. And the normal forces change its direction everywhere. I think I talked about this in the last lecture. So when we talk about power, right? So power is just a change in work for time, right? And we found that there's another way to write it. Remember that it was power equals, what was it? It's force dotted with, so power is a number, it's a scalar. Have I used that word before, scalar? All I mean by scalar is number. Scalars are numbers, as opposed to vectors, where you've got a list of numbers, right? So F dot V, that's your instantaneous power, but what do we know about F dot V? For F normal, the normal force. The normal force is always, well, by definition, right? It's always perpendicular to the track. The velocity of the ball is in the direction of the track, everywhere, even along here, everywhere along where it's changing direction. So the dot product gives you 0 everywhere. The upshot is that the normal force, just like the force of static friction, is always going to give us 0 work, right? So work due to the normal force is always going to be 0. That's a wonderful thing. Because it means that we don't have to, because think of how this wouldn't be such a useful solution approach, way to solve this problem, if we had to work out if we had to do some nasty integral that involves the work done by normal force everywhere, if it just didn't magically work out, right, that the track is pushing perpendicular to the direction of the motion in every single case. So that means we can do this. And that's great, because if I'm careful about my b's and a's, right, and I plug all this stuff in, we only have one unknown now, we have one equation, so we can solve for it. So if I plug all this stuff in, what do I find? I get 1/2 mv, so vb is what we're looking for, right, the final velocity. We said this was 0, right? The initial velocity was 0. I think we were told, yeah, initial velocity is 0. What else do we know? Oh yeah, we have to plug in for, so HA, somebody correctly pointed out, is going to be just mgb. Right? Oh, yeah, that's right. MGH, right? Is that right? Yes. I don't trust myself anymore. But then this, what do we do there? We have to add mg times whatever that height is. What is that height? Well, I can calculate it from whatever I was given in the problem, right? So is the height going to be bigger or smaller than r? Bigger, because of the way I set it up. Well, it's going to be smaller than 2r. There's 2r, there's 1r, there's 0, right? So I know the answer is somewhere between r and 2r. And in fact, it's just r plus whatever this height is. So to figure that out, I'll just draw a second triangle. I can draw on there too, but I might get busy. What I'm looking for is a height. So I want this to be a right angle right here. And I want this angle to be the theta again. This is the thing I want right here. What is that? It's going to be, which of these is r? The top line or the bottom line? Yes, the hypotenuse, the top line. This is r. That's good, because that means I can calculate this thing as r times sine of theta. Good. Super. So that means that this height, right here, just because of the way I specified the problem, is just r plus r sine theta. So that's all it is. But the thing is, if a problem is specified this way, a lot of students won't think to calculate the height. They'll look at this and think, oh, there's something about the angles. Nah, all you have to do is figure out what the height is, and that's what I need for potential energy due to gravity. So then this thing becomes r, if I give myself a lot of room, plus r sine theta. Great, so that's how to solve this sort of problem, right? And it equals 0, we put this on the other side. Notice that all the m's cancel, as so often happens in this class, right? All the m's cancel. There's g's here and here, but not here. So the g's don't quite cancel. And what am I looking for? I'm looking for v sub b. So if I say, okay, what's the final velocity? It's equal to the square root of this stuff. So it's going to be g times h minus g times r. In fact, I can pull the r out anyway. 1 plus sine theta. Anyway, so there's some algebra. But the bottom line is that we can get the answer. We can get the answer for the velocity. And because of the direction of the track, we can also answer the question of what the full velocity is, not just the speed of the velocity, because we know which direction you have to be moving just based on the shape of the track. But if we're asked another question, suppose another question says, how long will it take? How long will it take for the roller coaster to get from here to here? Well, using conservation of energy, certainly alone, it can't tell you that. Conservation of energy is a beautiful tool for us for solving problems, in large part because it doesn't require us to know anything about how long it takes things. It doesn't even care about what path it takes. Suppose I had a totally different roller coaster. Suppose I had a roller coaster started doing this, suppose it went the other way, and then cycled back around, and it did something, and then it came over, and the roller coaster winds up in the same height. Well, I would use I get exactly the same answer out. It wouldn't matter. The shape of the track doesn't matter. That's the power, conservation of energy, but it's also the drawback, depending on what you're trying to answer. So if the problem says, how long does it take for the ball to get, for the roller coaster to get to a certain place, you're not going to be able to get there with conservation of energy. At least not without combining with some other things. And in general, it's not going to be a helpful step toward that question. So it's good to recognize that you won't use it for everything, but you should identify when you can use it. I use it whenever I can. Like whenever I have multiple ways of solving a problem, it's almost always easier to use conservation of energy because you can skip all the intermediate steps, right? Okay, so yeah, so questions you don't answer, they got time. In the direction of the velocity, in general, you can answer. In this case, we could because of the constraint of the shape of the track. So, yeah, very good. Yeah, and so in general, right, what does this mean? I think you can probably guess what it means, and you've experienced this on your own roller coaster experiences. But if you start off on a roller coaster and you're at some particular height above the ground, right? Well, you know right away, no matter what this shape is, is the roller coaster ever going to wind up over here? Is it ever going to get? Is this roller coaster ever? If he starts off right, I want you to be clear. He starts off here, the velocity 0. So he's holding still. If you let him go, he starts and he does his thing. Is he ever going to make it over here? No, and that gives conservation of energy. Even if there's friction in the problem, that doesn't change that answer, right? Because friction, all that can do is take away. If there's suppose the wheels are rusty and there's some kinetic friction going on, right? Or it's a sliding block and there's kinetic friction on the ground. All that's going to do is suck away energy from the system, right? So that means that by the time he gets over here, he's not going to make it that height. He's going to wind up lower even. There's no way he's going to make it over the top, right? So this, I think most of you are familiar with it. I should do the ground. It's slanted, it's rather horizontal. But yeah, you're not going to get higher than you started. So like in the rotor cartoons as a child, it was really disturbing me, right? He'd be up on the cliff, he's got a giant boulder, he's being coyote, and he pushes this thing off the boulder. And I don't care, like, there's all these wonderful George Herman inspired shapes in those cartoons of all buttes and the funny. Doesn't matter what shape ramp you've got, you're not going to have that boulder come down, go through some U-shaped, minimum, and then come back up, and then hit land higher up, right, and kill the coyote. Even no matter how bad your luck is, right? That's not going to happen unless there's some form of potential energy in the problem. You've got, yeah, sure, maybe if there's a bear trap down there and the boulder lands on it, and there were episodes where that would happen. Okay, I can live with that, right? But it's not okay to have it like fall and then have it go in the air and he's in the shadow for a while and then the rock comes down, right? It's not going to happen. Doesn't matter. I don't care how nice it's run. Not going to happen. So yeah, that's the same idea. And this is of course very important for your chemistry classes and your biology because you ask questions about how close to the molecules, chemistry in particular, how close to the molecules get. We make the same kind of potential. So we can think of this as potential energy. So with it's gravitational potential energy in this case, but you can make other graphs, right? You can have some other kind of potential energy due to electrostatic forces between an electron and a nucleus or whatever it is, right? And there's a function of distance. Of course, this is complicated. Usually it's falling off steeply, right? But there's usually for a lot of cases you get curves that look like this, right? There's this really steep, tending toward infinity type of curve when you get really close. It's a separation, right? So whatever you want to call it, the separation between two charged particles. But then there's a something that goes like this, right? There's a sort of sweet spot. There's an attractive force and there's a repulsive force, and they're in competition. And there's a special distance away where the two particles want to be, right? A certain distance away. And you can think of it just like a roller coaster. It's just potential energy as a function of position, right? And where are you going to wind up? Well, if there's friction in the problem, this guy's going back and forth, and he's going to wind up on the local minima. That's where he's going to wind up. He's going to keep moving around until he dissipates all the energy in the form of heat in his wheels, right? And also sound. But that's a smaller effect. Most of the energy goes into heat, and warming things up. A little bit of energy goes into sound. Most of it goes into heat. We have a squeaky hinge. You can lose some energy that way. It's a smaller effect. All right, so that means so I'll do that. So this is demo. I think you guys have all seen this probably in one place or another. But so what about this? I told you that the normal force doesn't do any work. What about tension? Does tension do any work? So tension can do work sometimes, but in this situation, can it do work? So here's a case where I've got a bowling ball hanging from a string, right? And ropes only pull, so we know the direction of the force. Force is directly lined up with the string here, right? The rope. So the ball undergoes now some, it's going back and forth, it's pendulum, right? And we can use, in the same way we did with the roller coaster, we can use conservation of energy to figure it out. But we have to worry about a work term from tension. So what do you think? No. For the same reason we have to worry about it over there. So a pendulum always goes, the mass at the end of the pendulum always undergoes circular motion, right? Provided they're not lifting or lowering the rope. Now the thing is, if somebody's up on the ceiling, right, and they've got a rope, and there's a weight on the end, and they are hoisting it up, the rope can certainly do work, right? So tension can do work. It's only when one end of the rope is tied onto something that's not moving, then tension is doing work. So in that case, great, we're golden. And you know what I'm going to do? I'm going to crush my skull. I'm going to put this thing right here. You've seen this demo, haven't you? So, all right, so I'm going to put it right here. I'm going to close my eyes, and I'm going to ask no one to run up and push the ball. And the next, all right, we'll see if this works. I've got my eyes closed. You got to tell me if it's a... What a relief. Yeah, so that's conservation of energy. It really works. If you study this for a while, you start to believe it's true. That's really good. But anyway, so there's no surprise, right? But if somebody ran up, so suppose some uncharitable student ran up right here and pushed the ball, right? Then could it have hit me in the head? Yeah, it could. And that's because it would show up as an external work term. If I were to put up, if I were to do conservation of energy, right, for this thing, that would enter. And in fact, in general, forces of, me pushing on a ball, that kind of stuff, that's not a potential energy term, right? That's going to show up as a work term. One thing I should say too that's really important that gives students all kinds of trouble if they don't think about it explicitly, and that is I got a choice when I wrote down conservation of energy to solve this problem here of whether I was going to put potential energy due to gravity in here or whether I was going to put work due to gravity. Because if I want, I can think of it just as work that's done due to gravity, same thing. But I can't put it in both places. So when I have net external work right over here, if I put in mg delta h, where delta h is the difference between those two heights, well, for one thing, it would be negative or positive. So suppose for this problem, I say, what would the external work be? Did gravity do positive or negative net work on me when I go from here to here? Did gravity speed me up or slow me down? Want me to think about it when you go from up here to down here? Sped you up, right? Positive work. So gravity did positive work on me, or on the roller coaster from here to here. So if I'm going to have a net work term over here that represents what gravity did, which I can do if I want, then I would have mg, it would be positive mg, and then whatever the magnitude, whatever the absolute value of this difference is in height. But if I do that, then I do not include these terms over here. It's double counting. If I did that, I get the wrong answer. If I include these terms here. Another thing is, if you include the potential energy to gravity here, you'd better include it here, right? Unless it just happens that this is 0. And in fact, I set this problem up so that it's not 0 in either case, right? I set it up so that I made 0 down here. That means that this is non-zero and that's non-zero. So I got to include both those terms. So don't put it in all three places, and don't put it in just one place on this side. Either put it right here as a work term, or put the potential energy of gravity final here and potential energy of gravity initial over here. So don't double count. And the same thing for springs. If you have a potential energy due to a spring, don't put in a work to the spring. Now sometimes the problem will be phrased like you're asked for a work, and students are obligated to keep that work term around and stick it in and double count. Resist the temptation. You only want to account for it once. Potential energy is just another way to account for work done by certain types of forces, by conservative forces. And I think it's an easier way to think about it. And so I always, as a personal habit, I always use the potential energy due to gravity in springs as energies. I don't include them as work. I reserve this for non-conservative type work, for somebody pushing on the ball, for kinetic friction. That's what I reserve this for, pretty much as a rule, just so I don't accidentally overcount. Yeah, let me do a little more too. So that I like that demo. It's kind of dramatic with a big bowling ball, but I'll do this over here. Here's a smaller version of this thing, and I'll give you an extra little piece here. So once again, I made that comment a minute ago. See if I can figure this out. There you go. Is that gonna do it? Let's see. Oh, well, I guess that'll work. See if I don't get hit in the head. All right. Although it's better to get hit with this one than that. But so here's a pendulum, same as that, just smaller. But then here's another piece I can stick on. Right. So suppose I do this. Now, is it still the case in this case that the amount of work done by tension is 0 throughout the entire trajectory of the ball? Any opinions? Somebody's saying yes. Somebody's saying yes. What do you think? I think yes too. And the reason is that even though it's not undergoing circular motion, well, actually it is. At every stage of the way it is, right? This is circular motion with this radius, and now it's doing circular motion with this radius. So it's still the case that the direction of the ball is perpendicular to the force due to tension. So tension is not doing any work on the ball. So even more complicated trajectories, it's still the case. As long as this guy is tied on. If this were allowed to go up and down, then that wouldn't be true. So if I were going up and down with it, and I'm changing the speed of the ball, doing work on it, okay, fine. But as long as it's tied on up there, and so what does that mean? It means this is just like a roller coaster problem. Right? If I want to know how high is the ball going to go on that side, it's as high as it started, right? So if I know what this height is, well, it's going to be the same on this side. It's going to go the same height over here, right? It has to. Conservation of energy. There's no external work being performed except by a little bit of wind resistance and friction. So it is losing a little bit of amplitude. It's getting a little lower over time. Yeah, but that's because there are some dissipated forces involved that I couldn't control for. If I had a perfect ideal string, that wouldn't happen. Yeah. Yeah, that's a good question. So if this thing had no mass, if it were an ideal string, then it would have no kinetic energy. 1/2 mp squared, right, would be 0, because m is 0. But this does have a little bit of mass, and it is a little bit extensible. It can be extended a little bit, and when you get various, when it hits here and there's a force exerted on it in this guy, and of course, also the magnet moves, but we'll forget about that. So these things all can result in a little bit of loss of energy, because sure enough, the string heats up a little bit when it gets stretched a little bit due to a change in the amount of tension. So the string's tension is changing with time, and it stretches. When it stretches, it winds up losing some. It heats up a little bit. So yeah, and when it hits here, because it's not an ideal object, there's an impact. There's even a little sound that's produced that actually costs a little bit of energy, time of energy. Anyway, all these things add up, and it does lose. But if we're an ideal string, and if this were an infinitely rigid rod with 0, no kinetic friction, right, and all this kind of stuff, then it would just keep doing this, and there's no wind resistance, right? By wind resistance, of course, I just mean there's no force of the air opposing the motion of the ball. Then if all those things are true, it would just continue doing this forever with losing energy. But it's just really hard to build things that are like that. Turns out there are some things that are extremely close, in some cases even mathematically the same, like superconductors, and some straight you can have 0 resistance, right? But this is not an example that's that perfect. Yeah. So anyway, that's right. So in this case, no work is done. And we can think through why that is. So let's think about a problem we've already seen and solve it. And it's this problem right here, the shot and drop ball. So here's an example. It's got a spring. It's got gravity. It's got kinetic energy, right? And we can ask the question. Let's see. I'll do this thing again. So you know they're going to hit the ground at the same time, but we wouldn't be able to answer that question with conservation of energy. We wouldn't be able to answer whether they hit the same time or not. But we could answer the question. I'll just remind you what this thing does. So we could answer the question of how fast are they going when they hit the table. So suppose we ask, we know how quick something's moving. Well, what's the speed of the balls when they hit the table? Well, we know which one's going faster. Right? It's going to be this one. I'll just do what you guys want to do. Right? So they hit the table at the same time, but this guy's moving faster, right? And he's moving in some direction that's, depending on where he is on the parabola, it's some angle, right? If we don't care about the direction of motion, we just want to know how fast he's moving, then we can use conservation of energy. So let's think that through. And I'll do it a couple different ways. The way we did it before, of course, was we solved that using just constant acceleration equations. We have those kinematic equations. Before we got into Newton's second law, we had kinematic equations, right? And it allowed us to calculate how fast something's moving, how long it's going to take. We could calculate everything about it, all the things you might want to know, but they were a little bit clunky because we had to calculate along the way. So now if all we care about is v final, right? Then we can do it with conservation of energy. So what does that look like? The first thing I've got to be really clear now about the different times in the problem. So let's say at time 0. So here's time